This is Lab 3, Magnetic Field of a Bar Magnet by Thomas Reed. For an introduction to this lab, the purpose was to measure the distance dependence of the magnetic field due to a small bar magnet and compare these measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. The main concepts that will be utilized in this lab are the Biot-Savart law and the distance dependence equation for a magnetic field. For general results of this lab, n was equal to negative 3.5869, and the magnetic dipole was equal to 1.372837. And the equations are pictured on the right of this slide. For the procedure of this lab, the first step was to place a bar magnet at one end of an east-west oriented meter stick on axis, and then place the phone a few centimeters away, which was on the perpendicular axis. Then you would slide your phone slowly along a line perpendicular to the meter stick, being careful not to rotate the phone. Then you would find the position along this perpendicular line where the absolute value of the x component is at a maximum and the absolute value of the y component is at a minimum. Then you would rotate the smartphone 90 degrees and move it again along a line perpendicular to the tape on the table. Then finally stick a second piece of tape across the height of the smartphone as before to measure the magnetic field that was produced. The measurements and data that were collected were used with the Shell Excel spreadsheet provided. As you can see here, the numbers that came from the experiment, the distance, b of x, and then the off-axis field, and all the averages of these measurements that were found. And the trend line was y equals negative 3.8569x minus 15.538 in our ln of bx versus ln of r graph. For general calculations in this lab, we use the distance dependence equation, which, as you saw on the last slide, was y equals negative 3.8569x minus 15.538, where negative 3.8569 was the slope of the line, or n. Next, we used the Biot-Savart law to calculate the magnetic dipole moment. We solved for k, and b of x came out to be negative 15.538, where r was 1 meter, and then the natural log of k was negative 15.538, so when you solve for k, you get that number right there, 1.78 times e to the negative 7. Lastly, you solve for mu using the following equation, which is pictured on the right, and mu came out to be what was said on our previous slide, which is 1.372837. This is the glow strip model, as you can see pictured here, and the vectors that were produced from the code, and I will explain the code here in a little bit in further detail. So here are the four main parts of the code. On the top left, you can see creating the vectors for the experiment. The top right is creating all the necessary arrows that we wanted to see in our model, and then in the bottom left is creating the last part of the code, where we find the degrees of each dipole moment due to the magnetic field. In the bottom right, which is actually probably should have been the first thing that I described, because it's what is actually creating the dipole moment and creating the initial conditions for the code to run. So what if we hadn't oriented our experiment to compensate for the magnetic north and had instead laid out a meter stick at some intermediate angle with respect to Earth's magnetic field? So that when we accounted for magnetic north, the x component of the magnetic field started at 0 Tesla. If this had not been done, then the outside force of the Earth's magnetic field would have been interfered, making the x component of the magnetic field non-zero. Secondly, what if we were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The value of the magnetic field would increase from the current setup that we have. It could be a reasonable expectation that the magnetic field would close to double in magnitude. And lastly, possible errors in this experiment. The app that was used to measure this during this experiment could not have been properly calibrated when doing the actual experiment. There is also a possibility of human calculation error, and also possible inaccurate measurement due to lack of negation of necessary forces on the magnetic field.